Okay, so we are officially recording class. This is October the 18th, 2023. And so when we start looking at our schedule, today we're going to talk about something called regression analysis. We've kind of hit the meat of the order in terms of all the different geostatistical tools that can prove or disprove hypotheses. And we're going to talk about some of these today that are related to the factors that impact dependent variables. So what are all the factors or factor, we'll talk about it first, that impact dependent variables? One depends on the other. And we're going to look at some examples, some really rudimentary examples. And last week we focused a lot on some geostatistics, but the previous week you notice that all we did was we used GIS to extract out spatially related data, and then we ran our t-tests, and we ran our ANOVAs. And so our GIS analysis was pretty rudimentary. Select by location, find the centers in, let's look for these areas versus these areas versus these areas. So we can just kind of do a quick little dirty cut and paste. Last week, even most of the work that we did for death rates, crime rates, all that other stuff was developing the data, and then you click a nice pretty button and you get reds and blues and yellows. And if you look at the attribute for those reds and blues and yellows, there's not much there. You got some sort of GI star, which was that calculation that we looked at. I don't want to focus too much on that, but it turned it into some sort of z-score that tells us how far away from the mean it is. And depending upon if it was positive or negative, it turned it into a p-value. And then those p-values, if they were negative, really low p-values, they made them cold spots. If they were positive, really high p-values, they made them red spots, and then basically everything else was yellow. And so we had the pink to the red to the dark red, which represented 90, 95, and 99% statistical significance based on those p-values, which are converted from z-scores, or sometimes you saw the term in there, which were called t-statistics, which aligns with your z-scores when you don't know the standard deviation of the data. I don't want to get too much into that stuff. And so today, we're not going to have an assignment, All we're going to do is have an Esri assignment. So we're going to talk about geostatistics. We're going to talk about simple, very, very simple linear regression, things that you can do in ArcGIS Pro. And I've got a video here in what you can do using Excel. So to me, being able to set up the data, prepare the data, and then how do we interpret results? Because in a couple of weeks, we're going to talk about all the issues that you run into running these things. And I'm going to kind of mention a couple here as I go through this, as we think about it. And so the big focus today is going to be on case study number 5. And this is kind of a little bit of a precursor to it. And so now when we run age-graded death rates, and I think here we were looking at like heart disease or something like that. So we can see last week, I think we might have done some geostatistics on this, but you can run some geostatistics on this to figure out where the age-graded heart disease death rates are, which are hot spots and cold spots, which are high values surrounded by high values. What's the definition of high in this class? If I say it's high, what's it mean? What's a high value mean? Above the mean, well above the mean. Okay, and so well above the mean, surrounded by other well above the means. And then we talked about the definition of neighborhood. And part of that exercise that you did last week that you turned in, hopefully, or going to be turning in, in the next day or two, is going to be the idea of, well, if you change your neighborhood, that's not going to change the number of hot spots and cold spots, which I thought was really interesting, and so you can manipulate things like, hey, I'm getting hot spots here. I better change my neighborhood and maybe I'll get some more hot spots. Or I had too many hot spots to prove or disprove your point. Like we talked about with those two-tailed t-tests before, where I grabbed, another 5 counties and another 5 counties, and I kind of tweaked my study area a little bit. And so we turned things that didn't have statistical significance into areas, two separate areas that did have statistical significance. And so being able to play the system a little bit is your job to vet when we kind of review and look at all these things so we can prove or disprove hypotheses. That's the whole goal. So what we're looking at here is age-graded cancer. This is heart disease mortality rates here. And we want to see if there's any relationships to things like MED-HH Inc. What do you think this field here called MED-HH Inc. represents? Median household income, spendings on fruits, percent minority, diversity index, spending on medical bills. These are some things related to the food environment. This is called the Modified Retail Food Environment Index, which is the percentage of stores within each zip code that are classified as healthy. And so you can see the number of healthy stores, the number of unhealthy stores. There's a whole body of stuff that has yet to be discovered as to what's healthy, what's unhealthy, all these other things. And so you can go down some rabbit holes with these. So we're going to talk about the factors which help explain age-graded cancer mortality. So we're going to take a trip back to like high school geometry where we talk about things like y equals mx plus b. Does that ring a bell? Mm-hmm. Slope, y-intercept, all that other stuff like y equals 2x plus 3, but they're going to look a little bit different. Like y equals 23.7x minus 497, because instead of calling them x and y, we're going to call them age-graded rates, and our x's might be median household income. Or all of these together, where we start deviating from this nice simple 2 days to 3D and 4D and 5D and stuff that we don't really want to deal with right now. Some other things that I see here. Okay, so that's what we're going to talk about today. Next week, we're going to talk about spatial interpolation and density. So we turn maps that have dots in those into surfaces. And when I previously taught raster GIS class, I focused on those a little bit, but I've created a whole new chapter on this where when you have a weather map, how do you know what the weather is exactly, or the temperature is right where you're sitting? Is there like a weather station wherever you walk around? No. So how do you know?
Closest weather station.
Closest weather station. Or the closest weather station is going to have more of an impact than the ones further away. Now, we talked about that last week, where what's your definition of neighborhood? That you saw something called inverse distance weight. You remember seeing that for neighborhood? And so you had some options like, circle, neighbors, things that touch in corners, all those other things. So one of those 8 conceptualizations of neighborhoods was IDW, inverse distance weight. So if you live near the airport and the airport's temperature is 72, your temperature is probably close to 72. If you live further away from the neighborhood, from the airport, it's probably not going to be 72. It's going to be whatever it is near the station near you. Even though that 72 is going to impact it, it's going to weight it a lot less. So remember when we did weighted averages, imagine doing those big weighted average based on distance away and all those other things, if you can kind of think of that. So we'll talk about that next week. And then we're going to combine weeks 12 and week 13. And then week 13, we're going to kind of tie a nice bow on everything. While I talk about circumventing issues in GIS. Because today we're going to talk about independent variables, dependent variables, this thing called regression. Has anyone heard the term regression before? We'll talk about it. And we'll talk about one type called OLS, ordinary least squares ordinary least squares analysis. But how well does one variable explain the other? What have we looked at thus far? Statistical significance. Hey, let's look at the average of these versus the average of these. And to be honest with you, most of these are my go-to GIS and geostatistical tools. This is kind of up my alley. When we get into regression, it gets a little bit harder to explain because people who are really, really, really good at statistics, which isn't me, I'm just a GIS person who utilizes statistics, and just a few statistics, I think, can kind of blow you out of the water. So we'll talk about some of the caveats when we try to explain those. And after that, we got the final. So November 8th, in 3 weeks from now, we've got the final exam. And so we'll talk about that paper. And so those of you taking this class as an undergraduate student, you'll pretty much be done. If you have any outstanding assignments, you can turn them in on March 28th. But after that, all we have is the position paper. And remember, for that position paper, you're going to state something. You're going to prove or disprove something. Whether COVID rates are higher in, urban areas versus rural areas. Now, it's your job to figure out what urban is and rural and what test you're going to use. Or the clustering of heart disease death rates is higher in low-income areas compared to high-income areas. So I don't care about why. Haven't we talked about why with any of this stuff? That's for the education majors or social work majors or political. I don't care. We're the where people in this class. We figure out where all the stuff is. And the fact that data doesn't display a checkerboard pattern, I think that bodes well for us. Now, if hotspots for low income and hotspots for age-graded mortality rates are in the same place, well, there's something going on there. How does it impact? And today we'll talk about to what extent does it impact it? Can it be explained 10%, 20%, 50%? So we're going to look at a metric called R squared that also explains how well this kind of overlap exists. What are all the factors that impact this? So I'm kind of excited about that as well. One of the things that I did see with GIS and geostatistics, we'll focus on this one in a second here, but if you go to geostatistics and go to Indeed and look at geostatistics, you can see a lot of things here with geoscience, seismicity, GIS analysts with HDR, engineering, infrastructure, environment. So a lot of things with mining and geostatistics, but one of the ones that I thought was really neat here was this job here in the Poudre Fire Authority in Fort Collins, Colorado. And so I thought this was neat. You're the GIS analyst for the fire authority. I thought this would be neat because you're probably going to be outside. Pays $77,000 to $104,000. So that's pretty good. But in particular, it talks about the idea of using data and geostatistics or spatial statistics to assist with department decision making. Because at the end of the day, when we utilize GIS, we're really facilitating decision making, help to dictate decision making. When I worked with the military, they basically thought of us as the map makers. You all just make maps. And if you've taken, the intro level GIS classes, we basically cover the art and science of making maps in about 2 weeks, chapter 2 and chapter 3. What are the colors you want, legends, all that other stuff, because these days you can click a button and just export it to the web where it's going to look different on your phone versus this versus that. And your app builders and your web builders, they build all the minutia with the legends and everything else. And so the day and age of people like me taking a computer cartography class are long gone. We kind of just roll these up into one thing here. And so I thought this was a really neat job here. Some of the things I thought I saw was modeling to create digital and static products. So a lot of times we see the nice, pretty maps up there that you do create in chapter 3. What's the bar?
Do most of these institutions today use like ArcGIS?
Yes. She asked, do most of these use ArcGIS? Yes, but there's other GIS software packages out there that are going to look and feel the same way. There used to be one called Grass, and there's like an open source one out there. Like there's an open source statistical software called R. And I don't know if anyone's ever heard of that, but all the stuff we're doing in Excel, you can do in R and do lots of other stuff too. It's just a matter of just getting used to the environment. You can bring in the tables and do all this other stuff and then look for little tools to do it and helps and all those other things. So the things that we talk about in this, as well as GIS, have that. The thing about Esri and ArcGIS Pro, it takes over about 2/3 of the global market, even more in the United States. And the other thing about Esri is that we got a site license with the University of North Carolina system. So I'm not going to go and use other stuff if we're using this for free, using this for free. And so I thought this was neat. Risk assessment, fire. I saw something down here with you are going to go collect data, use statistical and analytical procedures commonly used in reporting. And so your descriptive statistics that we've talked about before. I also thought I saw some things about modeling. And so when we look at things like modeling, what do you think a model does? Like, what is a model? Like when we model things, we're getting deep here on a 515. What's a model? Yeah, like a representation of stuff, okay? And to me, I typed in the word model in your Esri training stuff here, and feel free to go and look at these. So if you go and apply for these jobs, you can say, hey, I took suitability modeling. And to me, there's kind of two different types of modeling. One of them I'm really good at, one of them not very good at. But things like suitability modeling I'm good at, where we can superimpose things on top of each other to basically figure out, I want to build a McDonald's right here. What are all the factors that go into it? Basically, this is called suitability modeling. Well, where do you want to build a McDonald's? One is where there's not another McDonald's, right? You don't want them competing against each other. Okay, what age, race, demographics, zoning are there going to be? Now, when we extract out zoning, because you can go to something, place called NC1 map and download every single parcel. So it's got to be a certain parcel size. It's got to be zoned certain. It's got to be near certain roads. It can't be near an existing McDonald's. And all these factors, so you can kind of stick it on and give it a score from 1 to 100 that says, this is the most suitable site. This is the least suitable site of the potential sites that you're looking at. Now, the other part of modeling is that I had fire in one location one day. Where is it going to move based on lots of other factors? And I'm not very good at that side of things there. So what direction is the fire going to go? Hey, what are the COVID rates yesterday? What are the COVID rates today? What are going to be the COVID rates tomorrow? How is avian bird flu going to spread? Because it spreads, all this stuff spreads geographically. If I'm in the same geography as you, I could potentially get avian bird flu, but it's not going to pop from one place to the other unless someone physically gets a plane and spreads it, which is still a kind of change in geography. So all of these things with modeling are geographical in nature. You know, we have volcanoes go into the atmosphere, and then where's the smoke plume going to go based on the rotation of the earth and how high it is and all these other things. So a lot of times you see some really neat visualizations, and we kind of call those modeling or computational modeling as well. And so feel free to go to the Esri tutorials and type in the word modeling and kind of check out some of the things there. So like Ariel said, we've got modeling, and that kind of gets into 3D representations. And so to me, modeling can mean a lot of things, but you know, in the modeling they're talking about with this site here is the whole idea of kind of prediction. You know, where is it going to go next here? But fire department data, standards of cover studies, project management. I think I saw something here. GPS concepts and procedures. Why would you use capture? Using my little phone right here. What would you want to capture out there? GPS. What kind of information do you want to capture? What are things that somewhere in a fire? And we showed another job this morning where you were doing asset management for a town. What are the assets they want to collect? They want to collect things like manhole covers and manhole covers, because that's literally theirs. Parks and all those other things. Are you going to use your phone to collect it? No, why not? Why not? So accurate. It wouldn't be accurate. Because, you have that little blue dot that shows up on your phone. It might be 50, 100 feet off. But we recently bought this thing here. This is like $3,000 here, And I'll show you some of the pictures I took from it. But it connects to this. And basically what we're trying to do, or I'm going to get someone else to try to do because I don't have the time or resources.
I'll do it. Experience with those things.
Oh, okay. But connect these to air quality monitors so you can collect air quality at the same time you're collecting this. And things like this will connect directly to your phone or tablet with ArcGIS, what's it called now, Collector, as well as like Survey 123. So these things have really high accuracy on GIS. Now the trick is connecting these to air quality and other things here, because I can just walk around and put it on state or whatever. You did survey.
Yeah.
Air, hey, I can just click on, okay, this is a manhole cover, but at some point in time, we want measurements taken with these. And then when we look at things like Survey 123 with asset management, we would largely, look at especially something like utilities, or maybe something like this. Hey, this is a dead tree. This is going to serve as, this is going to serve as fuel for that fire. Prior life, I was taking some PhD classes, and they did a whole class on like fire. I was like, this is pretty neat stuff. All the stuff that you didn't realize. And it was a program called EOS, Earth Observation System. So back then we didn't really have drones. So satellites and airplanes were getting a little bit more integrated to identify some of these features. But I thought this job was really, really neat. The other thing is the ability to organize and present technical information to users concerning applications, convey training information clearly and effectively to non-technical users and technical staff. Some other things that I saw up here, coordinates and projects with City of Fort Collins, Platte River Power Authority, Colorado State, Emergency Services Environment, coordinates regulars with managers. One of the things that this job, and you saw, was a pretty well-paying job, was the facilitation and development of soft skills. And that's one thing that I think I kind of lecture my kids about a little bit. But you being able to go meet someone from Larimer County or Larimer County telephone authority or whatever, and speak to them and know or pretend to know what you're talking about, and really kind of look people in the face and discuss with those. I was working with a PhD student the other day, and they're like, well, I'm introverted, I don't want to meet with them. And I'm like, I don't want to tell you, this is part of the job. And there's lots of people up there, the people who start making big bucks, like six figures and all these other things. They have the soft skills, they've got the writing skills, they've got the personal presentation skills, they've got the project management skills to back up their really good technical skills. And those are going to be the people that fill in the manager positions where you're making six figures. There's not a lot of GIS jobs that make seven figures. There's not a lot of $230,000 a year jobs out there. They're very, very few and far between. But when you start getting into management, you're like, low six figures. That's pretty good. I think we can all agree, if you're making low six figures, high five figures, by the end of your GIS career, that's pretty good. And our recent students who kind of enter the workforce, they're starting at 50s. $50,000 a year, $25 an hour, and kind of working their way up from there. So our students who, I don't know any advanced career students, and students who stay with it. If you're always moving around, that kind of doesn't bode well. But I can't stress the importance of kind of facilitating project, presentation skills, working with people, all these other things there. And, we're all quiet. I'm introverted. I could sit home and watch TV all weekend and not speak to someone. But when you got to kind of be game on with all this stuff, it's time to be game on. And I know you guys sound like your parents, and I've got, kids, in my house who they just live like this. I'm just looking at a phone. They just do this, and you look at them funny and they start twitching and all those other things there. And, you really need to kind of facilitate your soft skills, and take any and all opportunity to facilitate your soft skills, whether they're presentations, attending conferences, all that other good stuff. Or, hey, I had a student named Mike. You guys ever meet Mike Wallace? He was a graduate student. And we did a project with the DOT where he developed story maps and things called web experiences, which are kind of steps above web maps. And he ran the whole project. He worked 20 hours a week. We had meetings with the NCDOT, and He ran them, he met them, he did everything else. He took off with it. And those are the things that we look for. And so when we look at projects or we're meeting with other people, we're always looking for people who could be proactive as opposed to reactive, and just, this is, I'm going to take off with it. So like, our project we're working on, I've got about 7 different projects with people that we're looking at, that we're working on right now that I'm paying people for. And, if I have to chase people around to say, hey, what are you doing with my money? That's bad. And the same thing with these folks, you're doing training. So people who don't even know GIS, you're doing GPS, you're making maps, how to work with iOS and Microsoft Windows platforms and all these other things. So there's a wide range of technologies out there. And unfortunately, we don't have the time and resources to do this in a class that meets 2.5 hours every week for just 15 weeks. So take the opportunity to do that. All right, I'm going to stop sounding like your parents now. So, but take advantage of those, opportunities, because, at some point in time, it stops becoming what you know, it becomes who you know. You know what I mean? And, I'm going to remember that person, that NCCU student who presented at CDAG, or I'm going to remember that NCCU student that I met at that conference the other day that was talking about their research, instead of, someone who's, sending emails and all that other stuff. It's really easy for me to ignore emails, really easy. It's really hard for me to tell you to go away. I don't want to fund you, get out of here, or whatever, you know what I mean? And so those are things that we need to navigate in this kind of technological age, and I think facilitating face-to-face, relationships is important. All right, that's my tirade over. I don't think it was that bad. Okay, so today we're going to talk about the whole idea of predictive analysis, and so we're kind of migrating from inferential statistics to predictive analysis. All right, so some of the examples that we talk about is which variables best explain factors of bear sighting. And so we're going to talk about that research that I did with my brother. He was working on his master's. I'll explain a little more if I hadn't already, at the quadrant level. So we've heard this word quadrant before, right? The little squares and things like that. We know why we use quadrants, because they're equally sized and spaced and all that other stuff. Which variables best explain age-graded heart disease death rates at the zip code level? So that's what we're going to do for our case study today, because there's going to be no exercise assigned to this. But you are going to have a reading today based on a paper that Dr. McGinn and I wrote in support of the 2020 general election. What factors best explain by-mail voting rates in North Carolina? So you're going to go and interpret our results. Now, there's a lot of other things going on in the background that we need to deal with our data preparation. Just like the other day, a couple of weeks ago, when James said, well, what's your definition of urban? He said 15 miles. What if I said 12 miles? What if I said 20 miles? We might get slightly different results. And so not only as our definitions of urban, the preparation of data that we have there. Also, can the 2020 by-mail voting patterns be explained by 2016 by-mail voting patterns? And we'll look at these, because typically when we look at regression, this is what we're looking at here. We got a nice little graph here, and we have X's and Y's, so that can we see that your height, your weight is largely determined by your height, right? Taller people weigh more than shorter people. Can we kind of make that assumption? Yeah. Taller people weigh more than shorter people. And we could stick that into an equation right here. And so we have X is our height, Y is our weight. Okay, so Y is what we call our dependent variable. Y, that's why it's called Y equals MX plus B. So if we know X, we can just pop it in, multiply it times M, and add some sort of Y-intercept, and we get Y. So that's why we call it our independent variable versus our dependent or our explanatory variable. And so we can put this into a little chart here. So we're going to talk about what all this stuff means right here. All R squared adjusted, and everything else. Here's another one, meaning your time watching TV versus your grade. And so we can see what happens here. as your time watching increases TV, what happens to your grade? It goes down. And so we can look at data that does this, and we can extract this from a GIS. So with linear regression attempts to explain the relationship between two variables using a straight line fit to the data. Now, Excel, we can start to explain things using quadratics and polynomials and all that other stuff you probably kind of don't want to deal with in math class. But correlation provides the strength and direction of the relationship between relative position, and it provides corresponding values of variables. In addition, at some point in time, it's going to tell us, is there a relationship between these? Okay, so we're still going to have to remember these p-values. We talked about p-values last week, right? Anything in pink was p is less than 0.01 versus 0.05 versus 0.10. Did you look at that little table? I know you did, or at least you were supposed to. We got p-values out of those. Now, what did ArcGIS Pro software do? He just covered it. It just colored it in red. Anything in red had a p-value of less than 0.1. And if it was positive, it made it red. If it was negative, it made it blue. And so it's an estimation of the linear relationship between a dependent variable and an independent variable. And so we can plot these points and see how well they match up. And so height and weight, meaning taller people tend to be way more than shorter people. Now, there's going to be exceptions to those rules. This is an example that we did before with a former student, a biology student who sat right in the front here, where they want to look at EOG scores versus school attendance. Is there a relationship between school attendance and EOG scores? And scores of 1 or 2 basically are non-passing rates here. And so when we map it right here, this is daily attendance as our X versus percentage of people who scored 1 or 2. So basically, as attendance increases, our non-passing rates increase. That makes sense, right? Except for this one here, meaning that it had high attendance, but still a lot of people didn't. High attendance, it had high attendance, but still a high number of people didn't pass. Yeah, what is that called? What is it called? This point called when it's outside of all the other ones are. Outlier. So we got this outlier right here. What's going on there? They're still attending, but they're still not passing. So something's going on there or not going on there. And that's kind of where we leave it up to you. We'll talk more about this project later, or another project that a student have here. Now here, this is a map of convenience stores, accessibility or availability. We kind of use the term now, but you can see these areas in light blue. They're really, really close to convenience stores. I mean, there's one literally within 0.2 to 0.6 kilometers away. So we're talking like 1,000 to about 1,000 to about 3,000 feet away from them, while other ones, they're much, much further away. Now, if I were just to graph this, X is my per capita income, Y as my distance from my convenience store. This is what it looks like. Now, what does this graph tell you? What happens as your income increases? Do you get closer or further from a convenience store? You get further. Okay, we get further from a convenience store. Okay, and we're going to start to look in regression where that, if I were to throw a bunch of points up here, this is like 74 points. If I were to throw 74 points up here, what do you think the chances are that they appear in this pattern? Very low. Okay, so we're going to revisit those p-values. Remember, when we have really low p-values, that highlights statistical significance. And we can also draw what we call a line of best fit. And so now, instead of looking at like 2, 3, this point here is 40,000, 0.78. Okay, 40,000, that's $40,000 per capita income for this particular block group. And then 0.78 is the distance to the convenience store. So it looks and feels a lot like your old math class, but now we got different X's and Y's based on the units that we're working with right here. And so, but we also have a positive slope, meaning that as x increases, y increases, because previously we saw that as x increases, y decreases. And then we're going to look at other examples where that as x increases, y doesn't increase or decrease. So this explanatory variable, this independent variable, has no impact or effect on the y value. And so we've got different types of regression models. We're going to look at a lot of math, but I don't want to worry too much about those. And so we've got simple regression and we've got multiple regression. We've got linear regression and nonlinear regression. Excel actually, believe it or not, is really good at kind of doing nonlinear regression, meaning, hey, can it fit a curve a little bit better than it can fit a line? Because we know that some things that aren't going to be linear in nature. We have an equation like y equals x squared, where we got 0, 0, 1, 1, 2, 4, 3, 9, 4, 16. What happens to that y real quickly? It goes up because it's getting squared as opposed to being multiplied by a 2 or a 3 or a 4 when we deal with those coefficients. We also have something called multiple regression where we have linear, where we have planes. And probably in high school math, you didn't do too many equations for planes where you get into, well, 3 dimensions and 4 dimensions and 5 dimensions and nonlinear multiple regression, which we're not going to deal too much with. But when we have the equation here, it's y equals mx plus b. Right? Kind of rings a bell here. Y is the predicted value, b is the slope, x is whatever this independent variable is going to be that we plop in, and then we add it to a or b or whatever we want to call it here is some sort of y-intercept. And so we can predict these values. And so we can do these things with like biology, okay, suns, irradiances, all these other things so that we can kind of predict what they're going to be here. So we have some random error right here. So we have an observed value, we have a predicted value, and then we have some error attached to these. This is kind of what we look like. This has got a line here. As you can imagine, we might have things that look like that better fit these points right here. But they're all going to be explained using an equation. The most simple of these equations is y equals mx plus b. A nice simple line. This is easy, but I can explain it differently. Now, some of the other things that we do, I hate when I do this here. We can have these lines go parallel to each other, but we want to have what we call the line of best fit, meaning that our residuals are going to be minimized. And we'll talk about what that word residual means. Now, best fit means the difference between the actual y values, the predicted y values is minimum. Because in reality, all the values aren't going to be on that same line, just like we saw with the school prediction, the school prediction rates. We can get a good idea as that if this school has an attendance of this, we can tell you what the test scores are going to be, but they're never going to be exactly on that line because what are all the other things that impact school success rates? Attendance is one of them, but lots of other things. Some of those things are going to be quantifiable in nature. Some of these are going to be qualitative in nature, meaning, your kid woke up in the morning, was in a bad mood, and got a bad score. That's going to impact it. And that's something that we can't model, map, or store data on, especially at a kind of individual or what we call cellular level. And so we got all these equations here, but best fit basically means, y hat the average minus the actual value, and then we add them all up. And then we kind of throw it into all these nasty equations. The main thing that I want to kind of show you is that this is how we start to calculate the y-intercept. This is adding up the differences between the value and the predicted value. And this is what we call an iterative process, meaning we go through and do this hundreds and hundreds of times. Yuck, 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 yuck. No, what I care about is just, I want b. Y equals mx plus b. Give me the b, give me the slope. Because they're not going to be like y equals 3x plus 2. And so we've got a computation table. What I want is y equals 1.01x plus 4.436. This is a little different than when you saw in math class, and then r squared 0.97. And so what we're looking at right here is that drug calls versus drug arrests. Okay, drug calls versus drug arrests, meaning When there are no calls, we would expect to have 4.46 arrests. Why? Because if X is 0, we pop that X 0, and all we have is the Y-intercept, which is going to be somewhere down there. And so if we're doing some sort of crime analysis, if we get 6 calls, and then we do 6 times this number plus 4.46, this is the number. This is taken from real world data, and we have something here called R squared equals 0.97, meaning look how close these points are to the line. This is a really good model. So this R squared equals 0.97, which means that 97% of the variance in these drug calls or in these drug arrests can be explained using this model. This is really good. Most of my models are like 0.3. And so as points get further and further away, this R squared basically tells us how far away is the line from the actual points. Because when we look at linear correlation, we've got things like this is what it really looks like. You know? And so we have a positive correlation right here. We've got negative correlation right here. So as X increases, Y. So as X increases, Y decreases, or as X increases, Y increases. And then here, this is where we can apply things like Y equals X squared, logarithmic. This is like, the equation for this is like Y isn't equal to X squared, Y equals like negative X squared. You know, so it's like upside down. What shape does this look like? What is this? Remember this shape that you might have talked about in math or trig or whatever? Called a parabola. You know, a parabola. So this is an upside down parabola, you know, that you have like Y equals 2X squared plus 3X plus 2, Y equals 3X squared minus 7X plus 4, and what those things look like on the map get really ugly really quickly. Now, what we were talking about with our R squareds is that we have very strong relationships here. We have very strong relationships here where that our values are close to the line of best fit, where that weaker relationships mean that your points are going to be further away from those points. And then in addition, and this is another thing that people kind of confuse, even myself, I see something that looks like this and I say, oh, look at this. This looks really nice. But as X increases, what happens to Y? What are you going to say, Alondra? As X increases, does Y go up or go down? What's that? Oh no. Does it stay the same? Yeah. Kind of just stays the same, right? So does X have an impact on Y? No, not really. And so those are scenarios where they don't have an impact on anything. Now, the other thing that we talk about is residuals, because we know that when we map school achievement versus attendance, that they're not all going to fall on the same line. Nothing in the real world is going to be able to be predicted where we have an R squared is equal to 1, meaning it's all on the same line. Well, nothing in this class. And so the residual is the observed value right here versus the predicted. So we got an equation right here. So we could say if the vitamin D levels are 150, we can say that we know what the DSST score, or whatever we're looking at here, is going to be. Okay, or if it's 155, like it is right here. So this distance right here is what we call the residual. This distance is called the residual. And so we can map this residual right here. And all we do is subtract the observed minus the predicted. And when we have bigger residuals, our R squared goes down, meaning that this model, I've used this word model again because I think it can be used in a lot of different contexts in GIS. Now, what we're going to look at after the break is that how much can age-graded heart disease death rates be explained by the percentage of people who live below the poverty line? Meaning this, X is the percentage of people who live below the poverty line, Y is age-graded heart disease death rates. And so I just ran it through this in Excel. I get a nice little equation. This is Y equals 8.21 this plus 747, which basically means that if the poverty rate is 0, then the heart disease death rate, or whatever we're looking at, heart disease death rates are 747.2. That's all that it means. And so we've got residuals. So negative residuals means that the predicted value is a lot more than the expected values. Okay, so negative residuals are good, meaning that there's something going on there that it's not as high as what it should be. While we have something like this where it's 1600, but we predicted it to be 1123. So these are higher than what we would predict. So what's going on there? And so when I circle back to one of our students, what he did was he did some mapping of school achievement rates. And so he did this for like the entire state, and it was like high school graduation EOGs, and he brought in like hundreds of different variables to look at what are the best explainers for school achievement rates. And he didn't care too much about that, and he created this big old model. But what he did was he looked at the residuals. And so he looked at what are the schools that had negative residuals, meaning that they said they were going to have this school achievement, but they really had this school achievement, meaning they had negative residuals that said they should be a much higher than what they should be. So what are low achieving schools or high achieving schools that should have been low based on all the demographics? Or what are low achieving schools that should have been higher based on the demographics? And so he went and looked at those. What are those things going? Because to be honest with you, schools aren't largely geographic in nature. You got charter schools and all these other things there, as well as other things. And so we've got this explained and unexplained variation that we have here. Okay, so we've got this explained and unexplained variation here. Don't worry too much about this. Remember, this bar thing means average. This is predicted, because what I care about is how do we interpret this? And I've started throwing around this word p-value here. And so these will be the things that we're going to look at. Okay? And I've got a couple of these when I run these in Excel as well. And so I've got some of these sitting here in Excel. This is my regression example. This is what Excel looks like. If we were going to predict height using weight, this is one that I ran in Excel here. So I got height versus weight. I went through and graphed it right here. That's pretty cool, right? So if we can largely explain height using weight, using this thing right here. But now when I run it here, you can see I get an r squared value. I get a y-intercept. I get an x. And so when you see this negative 474, that's what we're looking at right there. That 9.506, that's going to be your m, your slope right there. And if I go all the way over here to p-value, I get a nice p-value right here that says 1.325 e negative 5. Okay, and then I get my, actually up here, I also get my significance right here, significance f. Okay, so I see these numbers right here that are really, really low, meaning that if I had 12 points, what are the chances I threw them up there and they made this exact pattern in a line or close to a line? Much, much less than 99%. Like, one time it's really difficult for me to throw nuts. So there's something going on between height and weight. Something. We don't know what, but we can model it. The one thing that we can do in Excel right here, I'm on the spot right here. But I can change my trend line right here. And so you see here, I've got this r squared. And in this particular example, my r squared is 0.833, meaning that you can explain your height, you can explain your weight using your height with like 83% accuracy. You can explain it with 83% of the variance. There's different ways to phrase that. And so 83. Now, what's the other 17%? Other things, genetic makeup, diet, all these other things that don't account for it. But if you know someone's height, you can get a good idea as to their weight. You can predict it with like 83%, accuracy. That's what this r squared means right here with this very simple equation. Now, I've done this in Excel, and I've got some tutorials on this, but I can change this. I can make this a polynomial. I'm just gonna click on polynomial. I'm gonna click on polynomial, and look what I got there. I got a nice little curve right there. Anyone see that curve? What happened to my r squared as I moved up the curve? Went from 0.83 to what? 0.907. Is that better or worse? Better. So now instead of explaining it using 83%, if I use this equation, now it's explained using 91%. So I just changed from linear, which I've been talking about, because what's linear? Just a line. And I changed it to this nice little graph right here that kind of fits these points a little bit better. Now I can explain it using 90%. Because there's going to be instances where we have kind of, now look at this equation, 0.5221x squared minus 60.617x plus 1, that masses, right? That looks like, that's kind of like a parabola right there, right? Not kind of like, it is a parabola. It isn't? I thought.
The exponential, if you want to do a parabola.
Oh, okay, exponential. Here's our exponential. This is weird because it's got an E right there, but yeah. And then we got our logarithmics right here. We got our polynomials. We got our powers right here. So 0.87, I won't do that moving average right there. But we got our kind of curved line, whatever we want of best fit. For now, we're just going to focus on that line of best fit right there. And because as you can imagine, for multiple regression, it's going to get really, really ugly, really, really quickly. But you can see our line of best fit is sitting right there. Okay? And then when I run and interpret it, this is what we look at, our significance right there. I'll show you another example and I'll kind of go and keep talking right here. But this is some of the school data that we were looking at. So this is the school data with the attendance versus the non-passing rates. And if I have it right here, you can see my significance right here is 0.0036. And my R squared is like 0.67, meaning that our school achievement rates can explain our school achievement rates can be explained using attendance at about 67%. So if we just knew the school attendance rates, we can predict it pretty well. Now, what are all the other factors that go into school achievement besides attendance? Lots of other things. And some of those things are probably going to be correlated or related to attendance, suspension rates, and all those other things, you know, that play into those. And that's the idea of what we call multicollinearity. You know, so if you're mapping two things against each other, well, you better make sure if you bring in multiple variables, you better make sure those variables aren't related to each other because they might just be canceling each other out. And so if we're mapping something versus race, let's map something versus white versus minority. Well, percentage of white is opposite of percent minority, so you're basically just canceling each other out. And so we'll kind of look at those in a couple of weeks when we run into those things here. But when we look at no relationship here, this is what no relationship looks like here. We've got these points. This is what no relationship. It's got an R squared of 0.02. And so it's got a slight negative slope. But when we look at the regression, you can see the significance is 0.67. Okay, remember, when we want significant difference, significance, this number's got to be really low. We just saw a couple here where one was like 0.04 or whatever. The other one was like 0.0000135 for those. And so make sure this is where we have here our significance here, and our significance here should also be this p-value right here. And so if you want to look at this p-value here, don't worry too much about that intercept. This is what we're more worried about there when we go and interpret these here. And so I'll start talking about that a little bit as well. And so when we start to interpret these, because this is what people get really kind of difficult about, is that we want to make sure we can explain one using the other without kind of using things like causal relationships. I don't want to say cause or whatever. And we'll talk more about those in week 13, where that, ice cream consumption causes drownings because they occur at the same time. No, they just occur at the same time. Okay, what are all the other things that go into it? So, without using X, how much can we predict Y? Okay, determine how much of the variability in Y can be explained by X. And that's what we said before. About 67% of that variability can be using school attendance can help predict school achievement rates. Slope determines the relationship. We've got positive slope, negative slope, or no slope, which indicates no relationship. And then that p-value, what is the chance that the x versus y is random? Meaning that I just throw these points up there. What are the chances that they're random? Just like we've already been looking at since week number 7 with nearest neighbor index. Those reds and those blues there, they're there because of what? P-value. What did it do? It gave a little bin right there. It said bin number 3, bin number 2, bin number 1, or bin 0, or -1, -2, -3. But all we're looking at here, and once again, we're just mapping p-values like we did last couple of weeks. And then we can measure the reliability in residuals. In theory, our residuals should be equally distributed here. And so real statistics people, they want to make sure our residuals are kind of like evenly distributed about the mean. We don't want to look at patterns like that. And then I think in week 13, we're going to talk about big words like heteroscedasticity. And it looks like a megaphone, or something called multicollinearity. And so all the caveats that people are going to say, hey, did you check for multicollinearity? Dr. McGinn's PhD dissertation did a lot of this work here. And so when we look at examples of R values, this is an R squared equals 1. This is a perfect linear relationship between X and Y. This doesn't happen in reality, even in kind of physical phenomena, because there's so many other factors out there that impact things, or that R squared is equal to 1. Okay, both of these R squared equals to 1. One has a negative slope, and the other has a positive slope. Typically, these are the things that we look at here. So we have some relationship here, stronger relationship here. This might not even give us a p-value that's significant. This probably will, because now when I revisit this map, this is what we're looking at here. We've got something like this. I went and made this nice little map here. I've got a simple table calculation because we're going to go revisit these t-values. But now I have an equation for the line of best fit is equal to y hat. The predicted y equals 2.9x point plus 2.7. Fill it in. How do I fill in 1 here? 1 times 2.9 plus 2.7. We just pop it in here. We multiply it times 2. We multiply it times 3. And so these are my values. These are my predicted values based on this equation. And then if I subtract the observed minus predicted, I get what we call the residual. That's the difference between the two. And so as you can imagine, if I'm working with decimals and things like that, this isn't going to be a nice decimal number. This isn't going to be a nice round integer right here. These things are going to fill in. And then look at this. Y is 17 for both 5 and both 6. And so here, if I have something with slope, as x increases, y increases here. So you notice this isn't going to be on a nice, pretty line right here. Okay. So this isn't going to be on a nice, pretty line. So what a line of best fit does is that it draws a line through these so that we minimize residual. I could draw a line of best, I could draw a line right here, but it's not going to minimize the residual. Okay, the residual is the distance from the line to each of these points. So all that nasty math that you saw before, all that did was go through an iterative process so that it can give me a slope and a y-intercept that represented these. And so now I can fill in this, and I can calculate a residual. Now, this is an example of some of the projects that we did. So we had black bear, and I talked about those before, right? Have I talked about my black bear project with quadrant analysis? It's not. Okay. They used to have yearly bear hunts. My brother started this for his PhD, for his master's at UNCG. He passed away. I found it amongst the stuff, and I was like, oh, let's turn this into a paper. And kind of you can see this because there was a bear attack. This is probably now like 2016 or so. And I don't know if anyone remembers Corey Cadell. He was a student here, but he's the student that works for Stormwater Division in downtown Durham. He lived like right in this area right here. And so when we make maps, the big problem is that when we make maps right here, the issue is that New Jersey is divided into townships and boroughs and counties and all these other things. And so that you have like these white areas here. Well, they're white here. They don't have any sightings. Why? Probably because they're so small. So it would be really cool if we created evenly sized units so that we can just look at the density or the count of these because they'll be one and the same. Have we ever done that before? We just create evenly sized units and superimpose it on a map? That's what we call quadrants. Why do we do quadrants? Just for that reason, so we don't get garbage like this. Now, the thing about New Jersey here is from 1995 to 2009 is that black bear kind of moved from northwest New Jersey all the way throughout the rest of New Jersey. And so we've had a lot more bear-human interaction, sometimes with fatal results. And so, where I grew up right here. I never saw a bear, but, once my parents left there in 2012 or something like that, they started to increase more and more. So they've had bear studies using geostatistics, using regression, using ANOVAs. Does all this stuff ring a bell? Regression, buffer analysis, ANOVA, like this is up our alley right here. And the thing about this is that the New Jersey Department of Fish and Wildlife, they publish black bear sightings at the municipality level. And so I went and requested those. There was about 4,700 points right here. So you can just see in the town, kind of the town where I grew up. This is where my high school was kind of right over here. My high school is over here. But the town where I grew up, it looks like a bunch of points here. Now, if we zoomed out, what do you think 4,700 points is going to look like on this map? 4,700 points. It's going to be big. It's going to be a lot. And so we did some range density analysis. We did some, range density analysis so we kind of spread out the density, or we did a count analysis. Basically, we just counted the number of bear within each one. I wanted to kind of spread it out a little bit. Sometimes we use the word smush. That's not a real technical term, but we smush these densities. Why? Because this might be the same person who calls on the same bear 50 times. So we're like, okay, or, this was, nuisance bears as opposed to just bear sightings. Well, there's a difference between nuisance bears, which are threats to people and property, as opposed to just bear sightings. How do you distinguish between the two? And so you can see I've superimposed these on my quadrants right here. And one of the things that I wanted to do is look at quantitative factors that explain these bear sightings. What are factors that explain bear sightings? And I looked at things like slope, elevation, distance to lakes and rivers, taken at the quadrant level. Okay, do I know how many people live here in this, in this quadrant? No. It's hard, and if I might have calculated population or population density, but these things are hard to calculate because these are calculated in like census tracts, so we can get an estimate, but it's not very good. But all these other things here, they're not stored in little squares. They're not stored in squares, so I can group these by squares. So I can look at things like percent forest, pixel variety. Has anyone heard that term? Has anyone taken, I know you did this in 4010 with raster GIS class, right? When we look at land cover, pixel variety is the number of different pixels in a particular area. Meaning if a bear has to go from forest to forest to forest to forest to forest to forest to lake, what are the chances of them running into a person? Really small. Now, if it's a bear that has to go from forest to develop to forest to develop to forest to a lake, what are the chances of them running into a person are higher. And so that's what we call pixel variety. And so I've got pixel variety here as well, meaning how many different types of land covers are you dealing with? Where it's, is it all lake? Is it all another? And so when I run these, I've got my t value, which largely aligns with my z-score. You can see these z-scores that we're looking at here. And I can kind of graph these right here, but I can see things like this right here. Areas with higher elevation will have more bear sighting. That's pretty cool. Areas that are closer to lakes will have more bear sightings. That makes sense, right? You live near a lake, probably bears want to go hang out there. The areas with higher slopes will have more bear sightings. The areas that are closer to open space will have more bear sightings. And so we kind of extracted some of this. Most of these are self-explanatory. Okay, quadrants with more types of land cover within it will experience more bear sightings. And so these areas right here will have more bear sightings. Why? Because it's just not forced. Chances of them running into people are higher and higher. We have other types of graphs right here. So this is your parabola right here. Here we can start to get into these nasty quadratics and everything. We get into this other one. It's been so long. Or your sines and your cosines. Your square roots, so these things are raised to the half power. And we have something here called logistic curve right here that can be applied to mathematical formula. Because now when we circle back to those factors that explain supermarket accessibility and convenience store accessibility using things like no high school, college, minority, white, median age, male, I run these against each other. And what we start to see is, hey, per capita income in dollars, it's got an R squared of 0.313. So basically 31% of supermarket accessibility can be explained. 31% of convenience store accessibility can be explained using per capita income. Really, really interesting. Meaning that, when we look at income, especially for convenience stores, you notice here with supermarkets, when we did this, there's not a lot of really high P values right here. Not a lot of high P values. With convenience stores, with supermarkets, you notice that they're near residential areas, but they're also near high rental areas, meaning, right here. Okay, here you can really start to see these P scores get vetted out, where that convenience stores are near rentals, near single parent homes, near low income, near high unemployment, all these other things. Now what does that do for people who don't have access to transportation? Where are you going to eat? I stop by convenience stores. I'm not paying $1 for banana when I can pay, 44 cents a banana, 44 cents a pound for a banana. And so a lot of times you see some of those things there. What's going to happen to your wallet if you shop at a convenience store every day? Eat at a convenience store every day. It's going to empty real quick, really quick. Okay. And so now what we can say here, especially with this graph, is that 32% of the variation in distance can be in stores explained by the variation in income. All the rest is unexplained. Now, last couple things I'll mention. It gets real ugly real quickly when we start to do multiple regression, because now we've got planes. Okay, so we've got planes that explain them. So now the equation is y is equal to b times b1 times x1 plus b2 plus x2 plus some random error. Yuck. Okay, so we create a plane that intersects it for 2 in 3-dimensional space. You got a little 3D. Now, what does 4-dimensional space look like? How do we want to deal with it? With 3 explanatory variables. So we're not. And so we'll look at an example, because at the end of the day, what do we want to do? We want to run this thing just like the geostatistics thing. We just click a little button. As long as we're kind of clicking the little button in the right drop down field, all the reds and the greens and all the reds and blues are going to pop up for us. And we say, oh, cool. And that's really neat, because it's just a nice map that's superimposed on our map that's ready to go. As long as you are extracting out the right data. You better be extracting out not population, but age-graded cancer mortality rates, or whatever else that you're looking at that's going to make some sense to the user. So how well do different variables explain age-graded death rates at the zip code level? Because that's what we're going to do after the break, where that we get all this stuff right here. Oh, yeah. Okay, and what you're going to do for the reading, and I'll probably talk about the reading after the break, and then we'll get into the exercise, is that we see little stars right here, and we see positives and negatives. And so some of the things we see is that I see right here, and I'm looking at this one right here. I'm looking at this one right here for those of you joining us right here. It's got an adjusted R squared of 0.21, meaning that positive poverty, negative home values, positive per capita income. That's weird. Okay. So as per capita income increases, death rates increase. As home values decrease, the other increases. And then as poverty increases, death rates increase. So we've got positive relationships. And the idea with the stars is that 3 stars is 99% significant. 2 stars is 95% significant. 1 star is 90% significant. Now, R squared. What does R squared tell you? Is R squared of 0.21 strong or weak? It's pretty weak. So what are all the other things that explain heart disease death rates? Where you were born, genetic predisposition, diet. Can we capture all that within a table? No. Okay. Now, some other things, when we look at these here, okay, you'll say positive relationship, negative relationship, and got the little stars here. This thing does, I think this thing is what we call a stepwise. And we're going to go through and do these, but when we run these model variables right here, this is what we care about, these p-values. So wherever you see a star, 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 significant. So poverty, home values, diversity index, have stars attached to those. If it's negative, it's got a negative relationship. If it's positive, it's got a positive relationship. So as poverty increases, then this other variable death rate increases. Diversity increases, decreases. Diversity rate index, this diversity index, decreases, death rates increase. So we got these little stars here. So at the end of the day, we care about these p-values or probability values. That's the stuff that I look at and care about. Now, this is for the research paper. This is for the reading this week. And what Dr. McGinn and I did was we went and extracted a whole bunch of variables to figure out what is the best explainer of by-mail voting rates for the 2020 general election. And I'm going to talk about this for a little bit because we focus this paper here, the reading a lot more on the regression than the hotspot analysis. Because we ran hotspots of by-mail voting rates. Where did people mail in? Literally never show up at a poll. They mailed it in the mail. Back in the day, mail used to be really good to get the mail and check everything. Now it's just all email and digital and everything else, and you just get junk mail. And then Amazon. And so we went and extracted all these things here, like by-mail voting rates, percent Democrat, percent Republican, all these things here. Some of these were easy, like percent minority, we can extract. In this case, it's non-white, poverty rates, median household income. Some of these got really ugly because these were extracted percent Democrat, percent Republican, extracted at the individual level, and then these are all grouped in zip codes. So all we're doing here is just running things like two-tailed t-tests and all that other stuff. And so we did hot spots of by-mail, hotspots of by-mail, or in cold spots of by-mail, and figure out, hey, is there a difference in income, poverty, minority between these? We've done this before with two-tailed t-tests, but this is the result of our regression analysis. And so we want to explain by-mail 2020 using about 10 different variables. Now, I got really scared when we got from one of the reviewers where they said, hey, by mail in 2016, you think the people who mailed in their ballot in 2016 are the same people who mailed in their ballot in 2020. Oh, crap, I didn't really think of that. That would have really stunk, you know? And so when I go over here, does it have a little star there? So what's it mean? No. And I was like, oh, goody, that makes me feel so good. And so what are the factors that explain it? You know, because basically we're going to create one of these linear regression models here where our by-mail rates of the 2020 general election, we're using lots of points. We got like 763 zip codes. So this thing's going to have 763 zip codes. Instead of having an X and Y, we're going to have like an X, Y, Z, A, B, C. So you can imagine this. We're doing this in multi-dimensional space, but the little stars are what? Population density and its power. So all that means is that where there are higher density people, higher density areas, they mail in their ballot. Probably because they don't want to show up to polling places and be around other people. Okay, median household income, where the income is higher, people mailed in their ballots more. Okay. And then we have things like percent minority. Now this is negative. So where minority increased, by mail decreased, or vice versa. Okay. And the other thing was average vehicles. And so areas that had less vehicles mailed it in more. Does that make sense? Yeah. If you don't have a vehicle, what are you going to do? You're going to have mail in the thing. Okay. And so I thought this was really neat. I thought it was really telling. It was close to percent Democrat, close, but not quite. Okay, because you notice this table kind of split it out at what? 95%. You know, they put the little stars there. But all we do is go and look for these little stars. And so what we're going to do after the break, when we'll meet back here at 6:30, we're not going to have homework this week, so I'll talk about the homework a little bit. I'll talk about the reading a little bit, because this is kind of Dr. McGinn's and I's kind of, it was a really popular paper, and it was kind of really low-hanging fruit. But we'll talk about this paper a little more. So you got a reading, and I think you got an Esri exercise to do, and then kind of finish up any of the other stuff that we got coming on, because we're going to be done in 3 weeks, and then all you have to do after that is the paper. So we'll meet back here at 6:30, and then we'll make sure you have case study number 5 open. And so we'll open up this case study number 5. We'll run a couple examples right here, and then we can get out of here by 8. So we'll be set.
Real quick.
Okay.
Of the database, actually, I've been doing some brainstorming. I wanted to run some numbers real quick.
Okay. I'm probably going to say yes, but go ahead. Go ahead.
So. Down here. I was thinking, so we have. Then 1.
Okay.
So really 1 is going to have like name, gauge, and type. So this is like a table that is going to be a table that's going to have only about 20 entries, 20 features. And it's just going to be a table for reference, all of the data that we're not collecting every month.
Good. Okay. I was going to say that.
So yeah, so a table that's going to have everything about the stores. That's just not something we don't collect every month. Just like name, location, type.
And then we could join it to.
That's what I was thinking. So yeah, so then this, this like,
And then we could just call it a table.
yeah. So yeah.
Now, the survey, basically, I was thinking for the survey, when you show up at the store, you'll have a drop down with all the stores that you go to. So you'll be like store, and that'll be linked back to location and all that other stuff. So you go to the survey, what store you at, click, price of bananas per pound, price of this per pound, price of that per pound, so that'll just stick it into that, so you might have 10 records from the same store, but taken at different dates. And we should be able to time stamp that or date stamp that, so you don't have to put that in yourself.
And. Great. So we have. We got Walmart right here, so it's joined.
Yeah.
So we got November entry for Walmart, joined to Walmart on this table,
Yeah.
and then December entry for Walmart, joined to Walmart on this table, and then this is.
Yeah, and it'll be a one-to-many join here, so basically, if we join it from this to this Walmart will appear multiple times, so that we'll have the same date. And so now, for price of bananas, you can. Right.
So I want it to be like if you select by. What is it? Select by,
Location or attributes.
yeah, so let's, so we wanna select by location and you wanna select, Walmart.
Mm-hmm.
Click on the Walmart, which right there,
And then everything will pop
I
up.
want it to spit out, all of the temporal data for it.
That'll be good. And there's neat, that guy Mike I was talking about, he did some neat things where he had neat pop-ups, customized the pop-ups that had, pictures of the store and things like that as part of the pop-up, and then it had customized the date, like date of bananas or whatever, so that output can be customized using arcade commands. I don't know enough about that.
I can educate myself.
Yeah.
But yeah, I just want to buy it.
That's pretty neat, yeah, because that survey one table only needs to be created once, you can just create it somewhere else. If you really want to get some data from them. Data Axle, it'll have that'll have information like the number of employees, sales volume, all that other good stuff. Oh, that'll just stay here, and then it'll be just linked to that. So is there a relationship between the average price of bananas and sales volume, the number of employees, or whatever, which are good indicators of space size? Yeah, I sounded smart there, didn't I? I think so. All right, cool. Let me hit the restroom real quick and. No, that's a good idea. How's it going? You're getting ahead of everything? Are you at work or?
I'm sorry.
Are you at work or?
Yeah, so,
Taking shifts?
yeah, soon I'll be getting off at 3:10. Yeah,
I report it and say,
yeah, that's what I've been having to do.
yeah, I respect working students and things like that. So we got a lot of challenges above the regular students who also have a lot of challenges, so. We've got about 2 minutes. We've got about 2 minutes here. And so what I want us to do is we'll open up this exercise called in-class exercise 5, case study 5. That's what it's called. And so if I go back to course materials, week number 10, we talked about predictive analysis, case study 5. I've got a couple of book things right here. We've got an Esri assignment, reading number 4 that I'll talk about. And I've got a couple of videos here where I do very simple linear regression. I'll talk about it in a second because I said. Okay. So what we're going to talk on, I can put you guys at me here. There we go. All right. There I am. Okay, so I'm going to sit at the computer here, drive a little bit. So when we look at week 10, I've got the week 10 topics, predictive analysis presentation that I just highlighted. I've got the video, so if you need to go back and revisit it. I want you to open up case study number 5, which is going to look like this here. And so what I've done is I've mapped age-graded death rates, and I think we're still talking about heart disease death rates for like 2012 to 2016 or whatever, so we can get a high and good sample size, because we understand some of the challenges with low sample sizes. Low sample sizes might create small number problems where we have really high or low increases, as well as when we look at margins of error. Like I said before, if I were just to say all faculty are taller, than faculty are taller than students, and I was just giving me against Ariel, well, I might, I think I'm taller than you, right? Yeah, okay. And then so, I won. And most of you can say, well, why don't you get more people? But I don't want to do entire campus because, well, that's going to take a long time. So we want an adequate sample size. And so when we run these two-tailed t-tests, it's going to say, hey, we've got enough so that we can create that normal distribution curve to make sure they intersect or don't intersect at an acceptable margin. And so I created that there. I don't know where I was going with that. So case study number 5. So we'll look at that. I've posted some textbook material from Sullivan and Mitchell. And then we've got the Esri assignment. I like this Esri assignment here. So this is an introduction to regression analysis using ArcGIS Pro. And so we'll have this due next week. It's just a nice little Esri tutorial. I like the stuff they use because they go and prepare their data nicely and neatly and all that other good stuff. But we will do a simple example here, so you will not have any homework related to this assignment here, but you have an Esri assignment, and then you'll also have a reading. And so when I think of it tomorrow, I'll kind of post that. Also, I've posted a couple videos on running simple regression and OLS. That's what we talk about. And all that means is ordinary least squares analysis using ArcGIS Pro. And then I do some very simple linear regression using Excel. Okay. If you notice in Excel, it doesn't do multiple regression. So you'll need to hit up something like SPSS, SAS, or R, which will do multiple regression. So if I type in the word R right here, I have something here called R Studio right here. And so R is basically another software package. Has anyone heard of R before? Okay, it's just another software package right here. But if I open it up, it used to be command lines here, but uh-oh, mind me later. Okay. But if I look at it right here, it's got a lot of things going on. I've got my test. Okay. I've got my data sitting up here, and you can see what it looks like here. I've got different variables right here, and then I can view, I can go to plots, I can add code and all those other things. So I can write R programs right here. So you can kind of look at the data that I'm doing here, and then I can type in, my commands right here that I want to run. And then I can also load things like libraries and others. So I can do my multiple regression and everything else. And these are just libraries created by the data user. And then we're going to look at reading number 5 here. Now, I really like this reading. This is a reading that Dr. McGinn and I did. And he's our kind of resident political geographer. But this was published in something called the Professional Geographer. So that's really official. If you're getting stuff in the Professional Geographer, you've kind of made it. And it's also part of the AAG. And so this is one of the books. It's published by the AAG, which is the Association of American Geographers, which is the largest geographical kind of society in the world. And so they have really neat meetings. Next month, we're going to be going to something called CDAG, which is the Southeast Division of Association of American Geographers. And later next year, the AAG meeting is going to be in Honolulu. So I've already submitted everything for it. And I already booked my hotel, and I'm going to be going. So that'll be fun, really fun. Okay, and so this is it here. And so you can see here, this is a brief statistical and geostatistical survey of the relationship between COVID-19 and by-mail voting in the 2020 election. The reason why I like this journal is because it's got a maximum of 3,000 words. The one challenge when you write papers isn't getting enough words, it's going over the word limit there, So to me, that's always the problem. So really being picky, choosy, and intentional about what's sitting in there and what isn't sitting in there. And you notice right here, I have a nice little introduction here, but using a working thesis that regions with high COVID-19 rates would have high by-mail rates. And so one of the things I like to do is I put a thesis in there right at the beginning that says, this is what I'm trying to prove or disprove. So sitting right here, I've got a null hypothesis. Okay, a null hypothesis sitting right there that we can kind of extract out. Now, I don't state that null hypothesis later, but I've got a null hypothesis. Okay, so my null hypothesis is that by-mail rates in high COVID regions equals by-mail rates in low COVID regions. And so basically I use a two-tailed t-test to prove, or in this case, disprove it so that I get a really small p-value. P equals 0.08 or 0.01 or 0.001 or whatever there. Now, what does low by-mail rate mean? I don't know. Where does high COVID rate mean? What does it mean? Above average. How do I express above average? And I did it spatially and I did it aspatially. And so you can see my lit review and all that other good stuff there. Methodology. This is my nice little map right here. And so basically in this map right here is that I did a quantile map, okay? Or a quintile map in this case means that all I did was each of these are evenly divided. And so all I did was I looked for all the areas in white versus all the areas that are darkest and looked for a difference in by-mail rates. Okay, that's all I did. So I kind of split them into fifths and just said, hey, let me look at all the areas in white which were low versus all the areas which are dark, which are in black here, and let me look for these. Now, this is totally aspatial in nature. Next. Look, does this ring a bell? What's this look like? Hotspots, yeah. Next, I did it spatially. So what does high COVID mean? Okay. Previously, high COVID was just, I had a list of all 763 zip codes. I listed you from highest to lowest and just said, I'll take this batch, which is the lowest, and this batch, which is the highest, and see if there's a difference between by mail rates. Next, what's this? This is spatial. You know? And so I took, let me look for the by mail rates in all the red versus all the blue. Now I go through and I somewhere in here, go through and do my little two-tailed t-test. You can see with the spatial one, there's no significant differences. With the hot spots, there are significant differences, but the significant differences are that the areas with low COVID have high by mails. It's total opposite of what I was thinking. You know, I was thinking that there's going to be opposite there. And you can see there are differences in September, October, which is a couple days before the election, and then even the emerging hotspots, which were basically percent change, or emerging hotspots, which were the areas that were level, that were yellow, that eventually became blue, versus the areas that were yellow, that eventually became blue. Those are called emerging hotspots. And so you see here, high COVID had low by mail with statistical significance. What are the chances that I average up 121 of these red hot spots and they're 9.04 versus 143 of these blue spots and they're 10.96? What are the chances of that happening? Really, 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 really low. So there's something going on there. I don't know what it is. Who knows? But what we eventually did here, when we started to get into the discussion, was, hey, what are all the factors that impact this? Boom, here we go right here. This is this table that we were looking at before. What are all the explanatory factors? And since Dr. McGinn and I went through the trouble of extracting out Democrat, and then we had metropolitan, micropolitan, and rural, we actually found out that the areas that had the highest COVID rates were actually like Democrat rural, thought that was interesting. And they also had the lowest by mail voting. Now, why? Well, I'm not sure. Did a lot of people have the resources to mail in their ballot? Why would you mail in your ballot? You have to figure out where it is, right? Where to mail it, all that other good stuff. And so some people may or may not have those resources to do so. And so, but this was neat because we extracted this from a list of like 7 million people, 7 million people. What do you think an Excel spreadsheet of 7 million people looks like? It's really, 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 really big. And so we grouped those by zip code. And while we were grouping those by zip code, we classified those as metropolitan, micropolitan, rural. And then, you got people in there, large, folks like me or whoever else, which are unaffiliated. And so there's a really large cohort of unaffiliated people as well. And so you can see these unaffiliated people actually by far had the lowest COVID rates, which I thought was interesting. And they had really, really high by mail rates. So it wasn't even like a Democrat Republican thing. It was largely like Democrat Republican, you're your own high COVID, low by mail, us unaffiliated across metropolitan, micropolitan, and rural areas are the ones with the low COVID and the high by mail. Even though you kind of see the Democrat metropolitan are trying to fit into this other box over here. Everyone get that? But to me, this is a really, really easy read right here. And Chris and I worked hard to make it an easy read that I think people in here could understand. So, and it's only 3,000 words. So 3,000 words isn't, it isn't that much, to be honest with you. So the questions here, you got 5 questions. They're worth 25 points. So each one's worth 5 points. So in trying to explain by mail rates for 2020, many may claim that rates that were high in 2016 were also high in 2020. So exploring factors such as COVID-19 and age were not needed. Using the results of the OLS, which of the following statements best describes that assumption? And basically someone said that. And so what I did right here was I ran that. I swear I ran it. Aha. Right here. You know, so someone said, hey, I ran an adjusted R squared. I just ran just because they wanted to. I stuck it into my model and it wasn't significant. But then I ran just an independent t-test or independent regression model or correlation or whatever you want to call it between 2016 to see if it explained 2019. And I got a R squared of 0.53. Is that significant or no? So it's just throwing a bunch of points up there of those 763. So that's the answer to the first one. But you can see these have a lot more interpretation, okay? So you can see our research hypothesis versus our conclusions. We ran OLS. Which of the following factors were not a significant factor? We ran OLS. Which of the following had significant negative correlation? Negative correlation, okay? And so these things, negative correlation, what's that mean? It's got to have a little star next to it here, and it's got to have a negative over here. I guess I'll put a little A right here, whatever, but it's got to have a star here and a negative here for it to have a negative correlation, okay? A negative significant correlation. Right. So those are some of the things that we've got there. At the time of the election, which group had the highest COVID-19 rate and the lowest by mail voting rate? And so I just want you to kind of make sure we understand these because, to be honest with you, most of the analysis, what do you think most of the work went into on this paper? Probably 90% of the work on this paper went into what? We made these maps last week, right? Didn't you just go click a little button? You click and then click on COVID and just, there it is. That's the map you all made last week. Most of it, 90% of it was going through and getting the COVID rates, which is probably 10% of it, but going through those 7 million records and finding percent Democrat, percent Republican, percent unaffiliated, and kind of cross-pollinating or cross-referencing those with our metropolitan, micropolitan, rural counties, and all that other stuff. That was the biggest pain in the neck because I got a list of 7 million people. Okay, Excel doesn't like working with 7 million records. Okay, ArcGIS Pro is not a big fan of working with 7 million records. R is, and so I knew enough R to say, hey, let's extract out the 3 million unaffiliated, and then I just ran a nice little summary so I could do a little spatial join and kind of group these by zip code. And so it's kind of working. You know, I kind of joke that I'm really fast, like pointer and clicker. You know, I'm fast clinger and pointer, that word, because I could just mess something up and redo it. You know, that's the best way to get these things right here. This isn't brain surgery. So I like this paper. This is probably one of my favorite papers that I've got out there. Okay, so next, we're going to be looking at this. We're just going to run a couple little models right here, run through these here. And so what we're looking at here is age-graded heart disease death rates right here. You can see where they're high and where they're low. Now, who made these colors? Me, I did. Based on what? I don't know, whatever the heck I wanted to, you know? And so if we really wanted to here, you know, and this is what we did last week. And so I'm just going to go through and revisit it really quickly, but I'll go through and revisit this really quickly. But when I go to my tools and my spatial statistics and mapping clusters, and I can kind of do my Gaddis ord right here. I'm going to kind of move you folks over here. I can map this because this thing is red just because of the way I classified it or grouped it or whatever here. I swear I know what I'm doing. Okay, so my input feature class is my zip codes. My input field is my age graded rates. I'll just run this fixed distance band right here. I'll just keep it as the default, but I'm going to run it here. And so you might get different ones here. I'm not going to focus too much on this, but this is kind of what we're looking at right here. And so now we can look at a cold spots, heart disease death rates, your hot spots over here, So, you can kind of see what we're looking at right here. So we got our hot spots and our cold spots. You notice here, this area right over here, it gets a little tricky here just because it's bordered by South Carolina where we don't have rates. And so how we define neighbor and all that other good stuff. So if I really wanted to, I could run it again with something where I do a fixed distance band, inverse distance. Okay, this is that inverse distance weight example that we talked about. So if Benjamin lives over near the airport and it says it's 72 degrees there, it's probably 72 degrees near his house. This gets a little bit weirder here. Look at these hot spots. And so basically what I did for my research was I put all the hot spots together, looked at the bi-male rates in the hot spots versus the bi-male rates in the cold spots, and extracted those out and found no statistical difference. Now, the other things that we have here are these other variables attached to median household income. And so if we look at the bottom here, median household income, percent minority, diversity index, spending on fruits and vegetables, average number of vehicles. And basically, I want to see what are the factors that explain this pattern here. Because I can go and map median household income. I can map diversity index. I can map poverty or per capita income and all these other things. And I can map those, look for co-locations on those. But it's not, all I'm going to do is see where they superimpose with each other. One of the things that I'm doing, I'm submitting a grant for with people up in math and physics, is that I have two maps that kind of superimpose on each other. What are the chances that they are co-located? Did anyone ever think about that? You could say no. That's okay. I do. Maybe they'll give me $650,000 to think really, really hard about that. That'd be cool. But it's something called what we call the Jacquard index. I don't know if anyone's heard that term before, but one of our recent papers that's sitting in week 13 is looking at the Jacquard index, meaning, okay, I've got I got this species and this species, and if I superimpose them on top of each other, what are the chances that they're kind of located near each other or on top of each other or totally separate from each other? Just like that nearest neighbor index, meaning if they're totally separate from each other, there's something going on there. Because if I put two species, they should overlap if it's perfectly random. And so you got to bring in sample sizes and all that other stuff. So that's just out there, but I have funding for 2 grad students and a PhD student. So that would be really, really neat if it worked out, but that's neither here nor there since I still have to work on the projects that I already don't do. But all right, so what we're going to do is run we're going to run OLS to kind of look to see if there's any relationships between these and this independent variable. So that dependent variable. So our dependent variable is going to be age-graded cancer mortality, age-graded death rates, or whatever we're looking at here. And we're going to see which of these factors can explain those. Now, we can pick out as many factors as we want, but I'll kind of let you know in week 13, we're going to talk about something called multicollinearity. So if some of these factors are related to each other, then you might run into some problems here. Now, how can we figure that out? Well, it's easy enough to figure out where that we can go and create things called scatter plots. Have we heard of scatter plots before? I think I might have shown these a little bit, but I can create new charts here called scatter plots. Oh, I already did right here. So I can create things between, I can create this scatter plot right here that looks at the relationship between percent rentals and spending on medical bills. So as the rental rates increase, the percentage of people who live in rental housing as opposed to owned housing increases, their spending on medical bills decreases. Okay, and you can see here this little thing here, r squared equals 0.26. Does that r squared make sense? Yeah. And there's probably a p-value attached to this, but this r squared, it really isn't that big of a deal, meaning that there's lots of other things here that kind of go into that there. And I can click on the little properties right here. And so I can look at things like this, relationship between, median household income and your average home value. Well, that makes sense, right? Areas where the income is higher have higher home values, right? That kind of makes sense, right? And you can see right here, it's got an r squared equal to 0.49, and it's got this y equals negative 28.5046 plus 4.1x. So this y equals mx plus b. It's showing up here in ArcGIS Pro. And this is a tremendous improvement from previous iterations or incarnations of our GIS software. It wasn't creating these scatter plots or any of these other things, because some of the things you could do is like you could literally go and highlight these points, and then they're sitting here right on the map. And so there's some interactivity between these points and these points as well. All right, so let's get to what we're going to do, and let's get out of here, okay? Because we got an Esri exercise and we got a reading. And so under map, under analysis, I'm going to go tools. And so mapping clusters. What we're going to do here is we're going to click on, what the heck are we going to click on? Oh, modeling spatial relationships, okay? So when you click on modeling spatial relationship, we've got tons of stuff right here. Exploratory regression, which is going to be a little different than OLS. Generalized linear regression, bivariate relationships, geographically weighted regression. We'll talk a little bit about that because all geographically weighted regression, all that does is there's another variable in there besides all these other ones related to location. And so you can see the 10 or 12 of these tools here. I've probably used like 2 or 3 of these here. So, to be honest with you, these tools are always increasing here. But we're going to click on this easy one here called OLS. So we're going to click on OLS. What's OLS give us? Okay. OLS give us our input feature class is going to be what? Our zip codes. The unique ID field is, I believe I created an ID. Okay. So I believe I created an ID. How could you create a unique ID field if you don't have one already? Yeah. This thing here, and it's got the little red star next to it. So the little red star is like, you better have a unique ID field. How can you create a unique ID field if you don't have one already? And watch what I did over here. I've got an ID sitting over here that I assume I created specifically for this assignment. How can you create a unique ID field? I'm making you all think on a Wednesday night. Any ideas? That's okay. One of the things, and then a lot of people don't notice, if you open up a feature class right here, you got something here called an object ID. This object ID is a unique identifier for this feature class here so that it can create a relationship between the table and the map. Okay, and so you call it a object ID, a unique ID, something like that there. So what I did was I just calculated a new field, did a field calculation from the object ID, because you notice when I opened this thing up, it didn't have object ID here. You notice that? It did not have object ID. Why? Because probably the program's like, don't mess with my object ID. You start messing with this stuff here, you start messing with this column here, things go bad quickly. And so it doesn't even want it in the drop down for it to write to or whatever. And so I just created a new field, did a field calculation. I said, whatever the object ID is, pop that thing in there. Okay. And so next, what do we have here? Okay, our output feature class is going to be least squares. Now my dependent variable is going to be my age graded death rate. Okay, I think it's called age grade rate. Okay, age grade rate. So you can see that column there with the 628 or the 777, whatever we're looking at here. And then we're going to try to explain it using a number of different variables right here. So we're going to explain it using a number of different variables here. All right, so variables, yeah, let's see what we got here. I'm just going to pick a few here. Median household income, spending on fast food, percent minority, poverty rates. LT1 means less than 1 times the poverty level. LT150 means less than 1.5 times the poverty level. So if the poverty level is $20,000, this is the percentage of people who live below $20,000. And then the other one is people who live below $30,000, or, median average home value, and that's about it here. In addition, I've got an output record file. This is pretty neat too. So I'm just going to save it in my case study 5 right here. So I'm going to just call this Tim's record right here, because I like looking at those things and see what they mean. And I'm going to run it. Because when you run it, you kind of get something kind of strange here. Okay. I got a nice little hotspot map. Cool. Is this what everyone got? And you can pick any variables that you want. I'm not too, emotional about these things here. But look what I got here. What the heck does this mean? I've been talking about y equal mx plus b and all this other stuff for a while. Now I can click on view details. Aha, look what I got here. Okay. And if I click on view history, now let me go back and let me find that file that I opened up. Here it is. Here's Tim's record right here. Let's see what it looks like here. What do I have? Okay, I try to explain it. Do we see any stars up there?
Yes.
Yeah. Under what? Average home value. Okay, average home value. That's the only thing that'll explain age-graded heart disease death rates. And is it positive or is it negative? It's negative. And so basically, as your home value decreases, what happens to the death rates? Increase. Okay. Now, if I were to use this, now I don't see anything here on R squared, so let me go back to my output here. Okay, all right. Now, when I look at this thing here, I've got asterisks, I've got age-graded rates, I got lots of other things here that I don't really want to focus too much on here, but I got an R squared. This R squared is about 0.16. So when I see these six variables, it only explains about 1/6 of the age-graded rate. What are other things that explain it? Stuff that we can't map, and a lot of times what people do, they start throwing more and more and more variables in there, and that really confounds things, because if we look at something like percent white and percent minority, they literally cancel each other out. So you're really not doing anything to the tool, and some of these things need to kind of be created with some practicality, because that student that I was talking about before he threw like hundreds of these things into a regression model to predict school achievement. And he's like, hey, the percent of Danish people is a good predictor of school achievement. And what are most of you going to say? There's not a whole lot of Danish people around, so there's probably a high margin of error with this stuff here. Danish people in the state of North Carolina at the census tract level aren't predicting that much stuff. And so, you got high margins of error. And it was Denmark. I'm like, what is Denmark? It doesn't. It happened to be part of the model that had a little star next to it. And he was pretty adamant about that. But so when we look at this isn't particularly very strong. I wouldn't call it strong whatsoever. Your adjusted R squared is, even further down at 0.1. And so the other question, the last question that I'll ask is, now what are we looking at here? It looks like a hotspot map, but now when I right mouse click and open my attribute table, this is what I've got. What am I mapping here? Okay, I'm going to X out of these here. What am I mapping here? We're mapping here the residuals. Okay, residuals. So I have an estimated what it was going to be based on what? This little equation right here. Based on this little equation right here with this slope and y-intercept right here. This is going to be my coefficient. And then if I actually go back to here, if I were to go back to here, if I were to go back to my processing, it would tell me that the little slope that I had here. So this was going to be my estimated, and this was my residual. So my age graded was 867. The estimated was 1024. So now we have this standard residual right here. And if I were to kind of look at these here, what do these things tell you? These things highlighted in blue, what's it mean? Okay, these have low age graded rates, which should have higher age graded rates. So these areas in blue are your outliers that are much lower than what they should be. Now, what do you notice about this one right here? What is the value? What is the age graded death rate of this one? 0. Why do you think it's 0? Fort Liberty. Fort Liberty. No one lives there, actually in there. So, where they were keeping different. So, that 0 really kind of skews things. What would you do to make a better model? I'd get rid of that one and run the model again and see what it does. And so we can automate that process. And that's what Dr. McGinn did in his dissertation. That's called stepwise regression. Now, Excel doesn't do that. You export this thing straight into, or you export these data, copy, paste into R. You can start running this stepwise regression if you want to. And this is kind of where my skill set stops. I'm not the best stepwise regression, just because people start getting emotional about multicollinearity and heteroscedasticity and all the other things that we have as a result. Now, last thing I'll mention here is now everything were these standard residuals, because these standard residuals, I believe these are going to be z-scores, so how far away they are from the mean. And so if I were to do sort descending, we look at these standard residuals. What are we looking at in these red areas here? Okay, these red areas are what? The age graded death rate is much higher than what was predicted based on all these factors, but mostly average home value. Okay. And so as home value increases, what happens to the death rate? Decreases. So where there are higher value homes, the death rate decreases. This to me, this is the textbook definition of what? Health equity or health inequity. Now there's a lot of other not nasty things, but things going on with the data, with the death rates and age graded to have a big enough sample size over the longest period of time or whatever. But this is, what we look at. And then some of these other factors, maybe spending on fast food, or maybe percent minority and spending, some of these things might have canceled each other out. So, you're kind of, getting a little sketchy with some of your results here. And so when we make these maps there, we don't care too much about the actual map itself, because all that is mapping is the blue areas or the areas below this line, which are lower than what they should have been. And then you're mapping the areas that are higher than what they should have been. That's all that map shows. So if you do want to show those, you can or whatever. But what I care about, me, and when you look at Dr. McGinn and my paper, what we cared more about was this. What are the factors that impact the age-graded death rates? It's 7:10 here. I'm done here. Is everyone else done? You guys all done too? Okay. So I'll post something tomorrow about what we got upcoming, but there's not going to be an official homework this week. Finish up any things that done. Usually I don't start marking stuff late. Some people ask for extensions because of some extenuating circumstances, and that's more than fine with me. But we'll have the Esri tutorial number 3, and then the reading, whatever reading number that is. What's that? 3 or 4? Reading number 4. And this is based right on this stuff that we do sitting in this department right here. So I think it's pretty neat. It's pretty neat. So I'll stop talking here. Everyone have a great day, and kind of should be good to go. All right, see you all later.